Welcome back to the Data Professor YouTube channel. My name is Chanin Nanta Sanamat, and I'm an Associate Professor of Bioinformatics. In this video, I'm going to show you how you can build a bioinformatics web application. And without further ado, we're starting right now. So in prior episodes, I have shown you how you could use the Streamlit library in Python to build simple web application ranging from a simple financial web application where you could check the stock price, a simple web application where you could predict the Boston housing price, a penguin species prediction web application. And so in today's episode, we're going to talk about how you could build a simple bioinformatics web application. And it is going to be based on the prior tutorial videos that are mentioned in this channel. So the bioinformatics web application that we're going to be building today will be an extension of a tutorial series where I have shown you how you could build a molecular solubility prediction model using machine learning, where particularly we are applying machine learning and Python to the field of computational drug discovery. And if you think of it in the grand scheme of things, it is part of the bioinformatics research area. And so this video will focus more on the aspect of actually building the web application. And if you're interested in how to build the prediction model on the molecular solubility that we will be using today, let me refer you to the prior tutorial videos on this channel, and the links will be provided in the video description and also the pinned comments of this video. Okay, and so let's get started, shall we? So we're going to go to the Streamlit directory. And then it's going to be located in the solubility folder. And so all of these are the actual files that we're going to be using today. And so actually, I think I have the prediction model on Google Colab. Let me download that. Okay, it's right here. And so this will be a concise version of the contents of a prior video where I have shown you how you could build machine learning models of the molecular solubility dataset. And so as I mentioned already, I will provide the links to this video. And so let's connect to this and let's have a look. So let me clear all of the outputs. And then it's already connected. And so we're going to import pandas as PD. We're going to be downloading the calculated descriptors directly from the GitHub of the Data Professor. And so this has already been computed as mentioned in the prior video. And so these are the computed descriptors: mole log P, mole weight, number of rotatable bonds, aromatic proportion. So these four are the computed descriptor from the prior video that I have mentioned. And the log S is the Y variable that we will be computing or predicting. And so these four variables are the X variables. Okay, and so we're going to separate this data frame into two sets of variables. One is the X variable, so we'll be dropping the log S column, and then we're going to have the last column as the index number is indicating here, -1, which is log S. Okay, so the X variables will be containing all of the columns except for log S, and the Y variable will be containing only the log S. Okay. And so we're going to be building the linear regression model here. And so we're going to import the linear model from sklearn, and we're going to also compute the performance metric by importing mean squared error and the R2 score function from the sklearn.metric. Okay, so let's run that. And then we're going to run the linear regression, and then we're going to assign this to model, and then we're going to perform the model.fit using the X variables in order to predict the Y. And so we will be building a training model here. X not defined. Okay, so I haven't yet run this. So let me do that first. All right, so let's do the model building. Okay, so the model has already been built. And then we're going to be performing the prediction. All right, prediction has been made and it is assigned to the ypred variable, and the prediction is made using the model.predict and then using x as the input argument. And then we're going to print the model performance here, and these 4 values are the regression coefficient values for each of the 4 input variables of the X, comprising of mol-log P, molecular weight, number of rotatable bonds, aromatic proportion. So the regression coefficient will represent the magnitude that each of these 4 variables are contributing to the prediction of the Y. So the greater the magnitude, the greater the influence of that particular variable. And so the y-intercept is right here, the mean squared error 1.01, the r-squared value 0.77, and then let's print out the model equation. Okay, so this is the equation. And then we're going to visualize the scatter plot of the actual versus the predicted. Okay, so let's run the scatter plot here. All right, so this is the experimental versus the predicted log S value. So as we have seen here from the r-squared, we're getting pretty good correlation between the experimental and the predicted log S values. And finally, we're going to pickle the object here. So essentially, we're going to save the model into a file called solubility model.pkl. And so we're going to import this into the Streamlit web application. And so we have already run it. And then we could simply click on this corner here and then click on the download file. Okay, and it's essentially the same thing that we have right here. But it should be noted that the version of scikit-learn on Google Colab and on the local version that I have installed will be different, and it will be giving some warning values. So it might be worthwhile to copy all of the code here into a file and then run it locally so that it's going to be using the same version of the scikit-learn. Okay, so let's think of that as a homework for you guys, and let's get started in building our web application now. So let's head over to the Streamlit folder, solubility, and let's have a look at the contents here. So the Delani solubility here, so these are the input descriptors comprising of the X and Y variables that we have been using just a moment ago to build the prediction model. So I'm going to provide you these files in the GitHub that is dedicated to this tutorial, and also the Jupyter notebook that we have seen just a moment ago for building the prediction model of this solubility data set. And so that Jupyter notebook will be using this input file here, but also in the code it is downloading directly from the GitHub of the data professor. So actually we don't actually need this as well, so I can just delete that, and then I'm just going to provide you the Jupyter notebook. And okay, so a total of 3 files will be used for this web application. So the first one is the logo. So this is the logo that we will be using for the web application. So I have drawn this in the iPad using the GoodNotes application. So here it is called Molecular Solubility Prediction App. So given input molecule, the machine learning model will be predicting the log S value. So let's fire up the Atom editor. Let's have a look at the contents of solubility app.py. Okay, so let's see. So there's a total of about 110 lines of code. And so notice that I have also included several lines of code that are essentially the comments here. And so these are just for ease of reading, having a look at what each block of codes are doing. All right, so if deleting the comments, it will be probably just under 100 lines of code. So let's take a look at the code here. Okay, so the first block of code that we will be using are essentially importing libraries that are needed here. And so we'll be importing the NumPy. And so NumPy will be used for the descriptor calculation. We'll be using pandas because we need to read in the data set. And actually, we will be using it to prepare the data frames as well in the generate code here. The function that we use for computing the molecular descriptors. So full detail, as I have mentioned, will be provided in a prior video that I have shown you in a step-by-step manner. And the hero of this tutorial is the Streamlit library. So this is the basis of this web application, and we'll be importing Pickle in order to allow us to save the machine learning model and then importing it in to this web application. And then we're going to be using the image function from PIL in order to display the logo that I have shown you just a moment ago. And here we'll be using the chem and descriptors function of the RD kit would be for computing the molecular descriptors. And the molecular descriptors are essentially allowing us to describe molecules in terms of their physical chemical properties. And so for ease of usage, we have already created the custom function for calculating the molecular descriptors, and they are provided here from lines here 12, which are the comments, until lines 57. And so we will be having two custom functions, aromatic proportion and the generate function. And let's take a look at the web application. So let me run the web application right now. Conda activate DP. You don't need to do this if you have already installed all of the libraries for your Python directly in the command line. But if you use Conda, then you want to activate the environment that is dedicated for running your data science projects. So I highly recommend installing Conda and then creating a specialized environment for your data science projects. So that will help us to maintain the library dependencies. Otherwise, if you have several projects on your computer and then when you upgrade one library, it might downgrade other libraries or other dependencies as a result, and then it might make some of your prior data science project not workable. So I highly recommend to use Conda and specialized environment for managing your data science project. Okay, so we have already activated DP here, and we're going to go to the directories, Streamlit, solubility. Okay, so we have 3 files here, and we're going to run it. Streamlit run solubility app.py. Okay, and now this is the web application. Okay, so the left-hand side here is the input parameters, which is the SMILES input. It will represent the chemical information of the input molecule. So each line represents a different molecule. So we have 3 lines here as an example, and you could replace this with your own data. And then we will be able to predict the value of the solubility as a function of the input SMILES notation here. So let me repeat this again. This portion, the SMILES notation here, each line represents a single molecule. So you're seeing here 3 lines, so it represents 3 molecules. And each SMILES notation will tell us what is the atomic composition of the molecule. And so here we see that the first line of code here, CCCC, it has 5 carbon atoms. And the second one has 3 carbon atoms. And the third one is a carbon atom and a nitrogen atom. Okay. And we can even search for SMILES of a molecule of our interest. And let's search for a molecule of our interest. Let's search for aspirin. And then let's click on it. And let's find SMILES. I'm going to search for it, Command F, and then search for SMILES, and we have it here in 2.1.4, canonical SMILES. So we're going to copy that. So this is the SMILES notation. And so I'm going to copy and then I'm going to paste it here. And then after we paste it here, we have to press Command and Enter in order to apply this. And then note that the predicted value here will be updated. So let's try it, Command Enter. Because I'm on a Mac, so I have to do Command Enter. And so on a Windows, it's probably Control Enter. And so here, we have the input SMILES notation, which is right here, the same thing on the left. And then below here, we have the computed molecular descriptors, which are the 4 physical chemical properties here, comprising of the mol P, molecular weight, number of rotatable bonds, aromatic proportion. So these 4 variables are computed using the RDKit library. Let me go back here. RDKit right here. rdkit, okay? So using the chem and descriptors function and using the custom function that we have written to compute the aromatic proportion, which is right here, aromatic proportion, and also the mole log P, which is the first column here, molecular weight, which is the second column here, number of rotatable bonds, which is right here, and the aromatic proportion is a custom function because rdkit does not compute that property. And so we will have to create our own function in order to compute the aromatic proportion. And so why did we use these 4 variables here? How did we know that we have to compute these 4 descriptors? It's because the original work by John Delaney, he used these 4 variables for building his prediction model. So if you would like for more information, please have a look at this original research paper. And so here, finally, we have the predicted log S value. And we have it predicted to be minus 2.0931. So this is the relative solubility value, okay? And so there we have it, a simple web application for predicting the molecular solubility values. So let's have a look further into the code. So image, this line of code here, 63, line 63 is this image. It is for displaying the image by essentially assigning it, opening it, and then assigning it to the image variable, and then using the st.image in order to actually display the image, and then use column width to be true in order to expand the image to fit the column width. And then here we're going to write out molecular solubility prediction app right here. We can even modify this to be like web app. Save it and then rerun it, and then you're going to see that the name is updated to be web app. And then these are the descriptors. So this is in Markdown format. So Markdown is allowing us to format text to have links, italic, or boldface as well. For example, if we want to make the text bold, we're going to be using double asterisk before and after. Okay, for highlighting solubility log S, we're going to add the double asterisk before and after. If we want this to be bold and also in italic, we need 3 of them. Click on always rerun. So you see that it is in italic, okay, and also bold. And what if we have only 1 italic? What happens here? So a single asterisk will make it in a italic form, and if we have 2, it becomes bold, okay? And if we want to add links to it, then we have the bracket here to define the boundaries of the text that we want to be linked. And then in parentheses, we're going to add the link, the URL here. And so you can click on this and it will take us to the original paper. Okay, and this is the original paper. It was published in 2004. Okay, so this block of code here will be reading in the input features, which is the SMILES notation. So st.sidebar header will be the header here, the heading, user input features. And then read SMILES input. So this is the example input that we will be using. And notice here that we use 5C. Let's rerun this. So 5C is right here. And then notice that when we have a \n, it becomes a new line. And then we have 3C, which is right here. And then we have a \n, which is a new line. And then it becomes CN, okay, which is the 3rd line here. Okay, CCC here, CCC here. And then CN and CN. Okay. And this is the input text of the SMILES notation. Okay, so the text box that we see here comes from this text area function, and the input argument include the SMILES input, which is the name of this right here. And then the SMILES underscore input will be the example SMILES notation that we have used here. So if we change this, we change the first one from C to N, and then this will be changed, right? It becomes N now. Okay, And then we're going to add a dummy first item here in order to allow us to simply read in multiple lines of smiles notation. And then later we're going to be skipping that dummy first item. And so we're going to do the same for multiple times on line number 91, 96, and also when we make the prediction. So this will allow us to simply create a data frame of the smiles notation and also for generating the data frame of the computed molecular descriptors for a single input parameter. So imagine if we have only a single molecule. Okay, this works, okay? But if we don't have the dummy items, let me show you, which is at 3 places, lines number 87, 96, 110. So let's save it. So without the dummy, let's see what happens here. Okay, and when we try to make a prediction, we get an error. Right here. Let's use, okay, so this is having, okay. It's skipping here. Okay, I have to hide this one too. 91 as well. So actually it is 87, 91, 96, and also 110. Okay, let's rerun it. So this will work, right? Oh, okay. So I think we're skipping. Oh, yeah, we cannot. Okay, we have to display X here. Otherwise, nothing will be shown. And then we have to display smiles here. Otherwise, nothing will be shown. See, nothing is shown here. And then we need to show the prediction. So we need to type in prediction. Okay, so instead of slicing from the second value onwards, we're going to have it printing all of it. Okay, now it should work. All right, it works now. So notice that it works if it has multiple lines for the smiles notation here. But what if it has only one? Okay, only one. Command enter. And now we have an error here. Okay. So for ease of handling a single input parameters, we're going to use the dummy item as I have mentioned. Right here. We're going to be reading the second value onwards. Okay. Now it works, right? When we have a single value here and we make a prediction, it works, okay? All right, let's continue. So I have already mentioned that we have the input smiles notation here, and the computed molecular descriptors is provided here in this block of code. So very simple here. So all of the hard work is done here in the custom function. And so we're going to be using only the generate, because generate will be using the aromatic proportion right here, aromatic proportion function. And then we're going to be using the generate function right here, line number 95. And then the input argument will be the smiles. And the smiles here will be what? It will be the input smiles that we have. Okay, so these will be the input, right? So it will be split according to the \n. So each line of code here, each line of the smiles notation will represent a unique molecule. Okay, and then each molecule will be computed for its molecular descriptors, and then it will be shown here in the X variable. So if we recall y equal to f of x, therefore x will be the input parameters for predicting the y value, which is the log s. Okay, and so the model has already been pre-built in the Google Colab just a moment ago, and we are loading in the model here using the pickle.load function and the solubility model.pkl. And then we're going to make use of this loaded model here, load model.predict, and then using the input x, which we have already computed here, right? So there's three major components. So the input smiles here is here. These are the example, right? But if we change this to something else, like aspirin, right? Then this whole thing theoretically will be here. Okay, will be like that. Okay, and then it will enter here, and then it will be subjected to descriptor calculation using the generate function. And then finally we have the x variables, and then the x variable here will be used as the input argument when we want to make a prediction. Okay, and so finally here, we're going to be using the computed molecular descriptors that are contained within the X variables. And then we're going to use the loaded model that we have already predicted, which we have already built on the Google Colab. And then we save it out using the Pickle object. And then we're loading it back into this Streamlit web application. And then we're going to be applying this built model here, load model dot predict. And then the input argument will be X, which are the computed molecular descriptors. And finally here, st.header is corresponding to right here, predicted log s values, and then the actual prediction will be shown right here, prediction, and it's going to be showing right here. Okay, so we could have multiple lines. Let's say that we have multiple input files. So here, let's say that we have multiple molecules. Let's change this to something else, so we are going to get a different molecule. And so we're going to see that the prediction value also changes, right? If we want to change a carbon to a nitrogen, what will happen here, right? So the log S value changes here. And so you're going to see that it influences the molecular weight and also the mole log P, but not the number of rotatable bonds and the aromatic proportion. So changing a carbon to a nitrogen is essentially changing one atom, and so it will be influencing two descriptors here. All right, so congratulations, you have now built a very simple bioinformatics web application, particularly for drug discovery. And so if you're finding value in this video, please give it a thumbs up, subscribe if you haven't yet done so, hit on the notification bell in order to be notified of the next video. And as always, the best way to learn data science is to do data science. And please enjoy the journey. Thank you for watching. Please like, subscribe, and share, and I'll see you in the next one. But in the meantime, please check out these videos.